Hello again, this is Galen Pickett, Cal State University of Long Beach. This is Physics 151, and now we're moving into a brand new principle, the energy principle. We've got another quantity that a physical system can have, like the momentum. It's changed only through interacting with its surroundings. So, it is section 3 of chapter 6 is what I want to give you. So, you read the whole thing, but that's what I wanted to give you some more insight into. So here I've got an object. If there's a force that's acting on it, it moves a distance L, and it has picked up a velocity v final. And let's say that this happens in a time t final. So there's t is equal to 0. And this is entirely a momentum principle problem that you could do. So let's see what the momentum principle says. Let's say that's the x direction. So I've got the change in the momentum of the system. And let's say that the system itself is the ball, is equal to the force from the surroundings, which is just F times delta T. So, putting in what we know, it's at rest to begin with, and then it's going with V final in the x direction. In the x components for the momentum system, for the momentum principle here, I've got m times V final minus m times 0, because it starts at rest, is equal to F times delta T. So I could even tell you, I tell you what the final velocity is. V final is equal to F times delta T divided by m. Well, that's interesting. This should remind you of the momentum principle average velocity position update ideas. So if that's what the final velocity is, then L is equal to V average times delta T. That's just the position update idea. If that's what the final velocity is, V average is equal to 1/2 V final plus V initial. So in this case, it's going to be F times delta T over 2m. So the distance that you go, L, is equal to F times delta T over 2m times the delta T. So now let's take a closer look at what this looks like. I've got something that looks like the final momentum here. Let's look at what the momentum principle says. P final is equal to F times delta T. I have a delta T squared in the numerator. It's very close to being the final momentum squared. So in order to have that, I would have to multiply both sides of this equation by a factor of F. So what I have is F times L, and that is a new quantity, we'll give that a name in a second, is equal to F times delta T squared over 2m. F times delta T is just the momentum that the system has in the final state, so this is P final squared over 2m. Another way to write this F times L, I'll give it a name, the work from the surroundings, and that's W, which is the force times L, is equal to P final squared over 2m, and then I'll write in here P initial squared over 2m, but in this case the P initial was 0. So what we've got here is a quantity that the system owns in a final state and an initial state. I could write this as delta E system is equal to the work from the surroundings. And that is the first simplest form of the energy principle that we're going to be looking at. The work from the surroundings is something like the force times the distance. So it's got units, force times length. A force is a kilogram meter per second squared times a meter. That's for the length, so I get kilogram meters squared per second squared, and we give that a name J for joules. The energy of the system, so that's the work side of the energy principle. The energy of the system, E, has got units of momentum squared divided by 2m. Now the 2 is dimensionless, so I've got the momentum is kilogram meter per second, and I've got a kilogram meter per second, but then I divide by a kilogram, that's this mass in the denominator, so the whole thing is a kilogram meter squared per second squared, which is the same thing as this joule thing. So the E here, I'm going to call this the kinetic energy, K final of the system, K initial of the system.